4 bonds. In chemistry, in organic chemistry, we're going to communicate not only in words but in drawings. And so we need to find a way to communicate with drawings that is relatively quick and also unambiguous. I don't want any confusion in our communication. And so we're going to take this video to really lay out the best way to communicate through structural drawings. Here I have a structural drawing of isooctane. So when you go to the gas pump and you see that number in the 90s, that is basically saying how good a fuel is this relative to isooctane. This is defined as 100 on that scale. Okay, so this is one drawing of it, and there are lots of problems with this drawing. First of all, it took me a long time to draw this. So before I turned the video camera on, I spent minutes, maybe hours, drawing this molecule. I had a giant beard, had to shave it again. It was literally the worst experience of my entire life, all right? I'm going to be drawing a lot of molecules if I'm going to be a chemist, and so I can't take the time to draw all of these H's and letters out like that. Secondly, you'll notice that this looks flat, and all these bond angles look like they're 90 degrees. None of that is true. This is not flat, and none of those bond angles are 90 degrees, and certainly not 180. That's ridiculous. So let's not draw things like this. Okay, so this is another drawing of isooctane. It has a lot of benefits over the first drawing that I drew. The biggest benefit is that the bond angles look closer to reality. Again, this is not the Platonic ideal of isooctane. It's constantly moving, these bonds are vibrating, so this isn't some sort of fixed object, but I can tell you that the bond angles are usually around 109.5 degrees, and even if this isn't perfectly 109.5 degrees, it's a lot closer than I had before, so that's a benefit. Also, this isn't flat anymore. Notice I've got this wedge, means that it's coming out at you, right? This is old school 3D, and this dashed bond means that it's going away from you. Okay, so when you look at this, the wedges are coming at you, the dashes are going away from you. And so you can see that these carbons are three-dimensional tetrahedral objects, right? Two atoms, two bonds in the plane, one bond in front of the plane, one hand behind the plane. Great, so looks a lot better. The downside is that this took me even longer to do. I don't have that kind of time. And friends, neither do you. Respect. So let's come up with a way to draw this molecule that is faster, that respects reality a little bit with respect to bond angles, and that communicates unambiguously. Okay, are you ready? Here we go. Done. Awesome, right? Okay, so how do we interpret this drawing? First of all, we remember that carbon takes 4 bonds. Each line here is a CC bond. Okay? So that's a carbon, that's a carbon. All of these points are carbons. And each line is a CC bond. I'm not going to draw out the letter C, and I'm going to assume that H's fill in the cracks. Okay? So when I see a carbon on the end here, I'm going to assume, okay, I know that carbon takes 4 bonds. It's got 1 bond to carbon, so I've got 1, 2, 3 hydrogens there. Here, this carbon has bonds to 3 other carbons. And so how many hydrogens does that carbon have? Well, only 1 bond left. How many hydrogens does this carbon have? 1, 2, 3, 4, so 2. How many hydrogens does this carbon have? Well, it's got 4 bonds to other carbons, so none. How many hydrogens does this molecule have? This carbon is bound to 1, 2 other carbons, So it's got 2 hydrogens there. It's a secondary carbon. This is the same. So are these. This carbon is bound to 1, 2, 3 other carbons, so it's got 1 hydrogen. This carbon also has 1 hydrogen. This carbon already has 4 bonds on the page, so there's no hydrogens there. And 1, 2, 3, 1, 2, 3 on the primary carbons. 18 hydrogens. Now, notice, here it looks like I've got this broken line here. So what's that about? That is a fancy art technique called perspective. So this is called a bridged compound because this is a bridge over that ring. Okay, so rings are okay. Even very small rings like triangles. Triangles are okay, right? The bond angle is a little bit smaller, which leads to some reactivity differences, but that is a stable molecule. This is a stable molecule. It can and does exist. Okay, so for this one, try to determine how many hydrogens it has. We've got 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 4, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12H. In general, if you only have carbon and hydrogen, you should not get an odd number. If you got an odd number, go count them again. How do we deal with atoms that are not carbon and hydrogen? We usually we always draw them out. So if I had an OH here, I would draw the O and I would draw the H. So when I say assume H is here, I should be more clear. Don't draw CHs. You can draw OH, you can and should draw OH, NH, SH, any other bond to hydrogen, just not CH. That is how we're going to draw quickly. Again, each line is a carbon-carbon bond. We're not going to draw CHs, but we will draw OHs and NHs and the like. Rings like this are okay, and so are bridges like this. When you see a broken line, those aren't 2 different carbons. That's just us using perspective.